Hello everyone. So now we'll be again taking up the topic of expectations. Okay. Just again the definition. So what is the definition of expectation? So if we have a random variable x, so we write expectation of x like this. So then this random variable will take some values. So now we are in the realm where we are discussing this discrete random variables. So in that there will be discrete values, or we call them finite or countably infinite values, or countable infinite values. So this is what this discrete random variables take as values. Okay. So how do we write these? So we write, let's suppose this discrete random variable takes value of x1, x2, x3, and x4. Okay, and this x1 with the probability of p of x1, and accordingly for these variables. So how do we write this? So we'll write it as x1 multiplied by probability of x1. Okay, and this over here is probability mass function. So this is the probability mass function. Probability mass function. And then plus we write x2 multiplied by probability of x2. Okay, and so on. So in succinct way, we wrote it like this: probability of xi, I goes from whatever values it takes, 1 to n, let's suppose, and this is countably infinite. Probability of xi. So this over here is probability mass function. So what did I tell you about expectation? So expectation was just a number. We wanted a summary of the thing. Okay, if we have a random variable or if we have a distribution, can we come up with numbers which can summarize the whole details? So let's suppose if you are talking about these distributions and these PMF, they give you a lot of detail. They give you almost every detail. But what if I just gave you one number and you were able to guess something about that? That's what his expectation is. So these are numbers which I in the previous lecture I think I just told a number called as the sensory variables. So what are these sensory variables? So sensory variable means they summarize it. Okay, if I give you these values, you get a good idea about the distribution. You get a good idea about the random variables. So that's what these expectations are. So this is the formal definition where we write it like this. So these are also sometimes called as weighted sum, or average, or a center of mass. Okay, so let's see why are they called so. Okay, average, I hope you guys will be able to guess. Let's suppose I'll take an example and then I'll explain it with that. Okay, let's suppose you are rolling a die. Okay, when you are rolling a die multiple times, so let's suppose you got 1 on the first die, then 1, then 3, then 1, then 4, then 3, then 2, then 2, and then 4 again, then 3, something like this. Okay, so if I will tell you at average which number are you getting? Okay, at average which number are you getting? So what you will do? Let's suppose this can be rolling of a die, rolling of a die, or maybe let's suppose if you are playing a game, so football. So number of goals that a player scores. If you are playing football, so that in that game, let's suppose these are the number of goals that let's suppose CR7 is scoring on that match, in that match. So these can be any examples. Now abstracting out the details. So this is the data that you have. This may be an experiment. This can be a match. Okay, this is what you are doing. If I am saying to you in terms of this football, so what's the average number of goals? Okay, what's the average number of goals scored by CR7? So what you can do is you can easily take it like this. So you can take this 1 plus 1 plus 3 plus 1, and you can add all the things and divide by the total number of observations. That's 1 2 3 4 5 6 7 8 9 and 10. Divide by 10, whatever the number comes will be average. Let's call that mu. Okay, and we call it average, or let's suppose mean. Okay, so can somebody calculate this average? This is the average. So this is 5 6 10 13 15 17 21 24. This is 12. Just correct me if I'm wrong, huh? No, 1.2, either 2.4 rather. Okay, this is divided by 10. Is it 2.4? Check it. Okay, so the average value is 2.4. Okay, so that's the meaning of average. So I can compute this average in some other sense. So let's do that. So how can I do that? So 1 appears 1, 2, and 3 times. 1, 2, and 3 times. So I can write it like this. So I can write number, that's 1 number of occurrence of that number, frequency basically. So I can write frequency. Okay, and the total number is, I have counted 10 times. So this is 1. So 1 appeared 3 times, and then 3 appeared, see how many times? 1 2 and 3. 3 appeared also 3 times. 4 is 2 times. This 4 is 2 times. And then 2 is 2 times. Okay, so I just wrote the frequency. So what I can do is now, so I'll compute the probabilities over here, or maybe I won't name it probabilities. What I'll do is I'll compute something like this. So 1 multiplied by 3 divided by this 10. So I'm taking this divided by 10. So I'm taking the weights, because out of these 10 times, this 1 came 3 times. So what I'm writing is I'm saying 1 multiplied by 3 divided by 10 plus. So then I'm taking 3. 3 multiplied by 3 divided by 10. Okay. So over here, this is the number and this is the weight that it has. How many times it occurred divided by the total number of times. We had the total number of numbers, and then we had 4. Okay, then we can just multiply it by, so let me take it here. So this is 4 multiplied by 2 by 10, and then plus this is 2 multiplied by 2 by 10. If you compute this again, it will come out to be mean, but here we call it weighted average. How many of you understood this? So this again is the same thing. So if you just collect these things, so this will be same, because the denominator will get, you will get 10 and divide by whatever you had. 1 3 times, 3 3 times, 4 2 times, and 2 2 times. This will again the average. Okay, this will again be 2.4 if this number is correct. Okay, so this will be the same. But here if you see the calculation that we did is, so we took this number and here we took its weight. So we call this weight. Okay, and again this is the weight. That's why it's called as weighted average. Weighted average. This again is an average, but it is a weighted average. Okay. Now what an expectation is? Expectation basically is in weighted average, where these weights are actual probabilities. Okay. So these weights are actual probabilities. So weights are probabilities. So how do we come to know about these probabilities? By using the probability mass function. Okay. So that's what these are. So if you go back to the definition of probability, what a probability means. So there we say, let's suppose when you have probability of head, you write 1 by 2. So what's the meaning of this? Okay, the frequentist approach says that if you toss this coin, let's suppose if you toss a coin that is unbiased, and if you toss it enough number of times, so you will see that half the times head will appear and half the times tail will appear. But what is this enough number of time? Okay, so basically if somebody tossed it 10,000 times, okay, and you can see that he might get half multiplied by 10,000 times, around that he'll get heads. But it's also there is a probability that he'll get tails till 10,000. So there is nothing that stops this. So there is the probability, there is some probability, but this probability is very low. Okay, but in mathematical sense there is nothing stopping this from happening. This can also happen, but this has very low probability, but it is there. So what I'm saying is, so when you assign a probability towards this, so you are assuming that it comes from underlying distribution. So there is an underlying distribution. There is an underlying distribution. That's a real distribution that nobody knows. Okay, nobody knows that. Then what we do is, the only thing that we can do is we can collect data. So there is an underlying distribution that nobody, if the people know this distribution, then the game over. Then we have nothing about, we should not do machine learning, we should not do probability, because everything is known to us. Okay, because the lack of knowledge that we have and the things that we have, we cannot know this underlying distribution. We cannot know the actual PMF. Okay, this underlying distribution is not known to us. Then what we do is, we do a process called as sampling. Okay, by that sampling, we'll just collect some samples, or we'll perform some experiments, and we'll collect the data, and from that data we'll try to estimate the actual distribution. Okay, let me bring it into the real world. Why am I talking about this? I'll just connect it to expectations. So you have an underlying distribution. Okay, underlying distribution of, let's suppose, height of people. So when the God is creating humans, so there is some distribution it follows, because if a person is if this process is deterministic, this is deterministic for God. Let's suppose God is supernatural entity, she knows everything. But for us humans, it is a probabilistic process. Why? Because we do not have a lot of knowledge about the process. Okay, if we knew all the things that are involved in that, probably we'll be able to tell with 100% accuracy that the born person will have this much height when he becomes an adult. Okay, that we can see. But the problem is that we do not have access to that distribution. There are a lot of unknowns for the humans to know. Okay, there are unknowns which we cannot even know, and The first task is to what are the things that affect it. We probably are not equipped with that also. Right now we do not have these many number of things. Okay, that's why we bring them this probability. We say that okay, there is uncertainty, and even with that uncertainty, I don't have control to control that uncertainty. Now the thing is, let's deal with the probability. So there is some underlying distribution. So somehow the heights are following a distribution that you don't. It may be a complex distribution. Okay, as you saw at simple distributions like Bernoulli distribution, binomial distribution. So there are simple distributions which we brought into mathematical world and we can analyze them. But a distribution can be more complex than that. And that distribution is the underlying distribution. That is the real distribution, the actual PMF that follows. Okay, that will be a deterministic machine, and all these variables taken together, and God will probably feeding that all the characteristics of a person into that machine, and it will give the height with 100% accuracy, and there will be no inaccuracy. But you know that here we assume that we do not know this underlying distribution. So that's what I'm saying, always and always. So if we know the distribution, there is no need for machine learning, because you know now you have everything is deterministic for you. Okay, so then why should you learn? Because you know the distribution. You can just have a hard-coded thing and you'll get to know everything. Now you have this underlying distribution that you cannot know. And what you do is you do sampling. You take some samples. So when you take the samples, so then you try to estimate the actual distribution. Okay, let's suppose the underlying distribution for this head and tail is 0.5 and 0.5. This is the probability distribution. Okay, that is 0.5 times head will appear and 0.5 times tail will appear. That's the underlying thing. Let's suppose somehow we got to know this. Somehow God came and just he spoke this into our ear. Hey, look, the probability of the head is 0.5 and the probability of tail is 0.5 for this coin. Okay, now what we can do is, okay, so we have to ascertain this and we have to see. So you can keep on, you'll keep on performing experiments. So you'll keep on performing experiments. Basically you will do sampling. Okay, you'll just flip the coin and you got head. You'll flip the coin, you got head. You'll flip the coin, tail, head, tail, and so on. You'll keep on doing it. Let's suppose first you do 100, you did this 100 times. So when you did it 100 times, we'll call that, let's suppose we have an experiment or we have a sample 1 in which we had 100 samples. Okay, so this was our first sampling, first sampling when we did the experiment 100 times. So what you saw is you saw 30 times head was there and 70 times tail was there. So this is what you collected. So now you saw that probability is 330 by 100 and then 70 by 100. Then you saw okay, let's do one thing, let's do some more experimentation. So then we'll do S2. S2 means you're again sampling, you're sampling more. Now let's suppose you collected some 1000 samples. So when you collected 1000 samples, this means that let's suppose now the number of heads is 360. Okay, and the tails is 640 if my calculations are correct. So this is the probability. Okay, if I now compute the probability, this is the probability that I am writing it for here. Okay, now again, now you know that this is the real distribution, this is the actual distribution. But since you are computing this continuously, that's why I said that you have to do this enough number of times. Once you approach this, once this number is quite high enough, you will see that this sampling, it approaches to the actual PMF, or it approaches the actual distribution. Okay, that you can do it also within your computer simulations. Okay, you can just randomly generate numbers, and then you will see if you have to generate this 0.5, let's suppose head and tail. In each iteration, you are generating head or a tail with equal probability. Then within, let's suppose 10 experiments, you will see the probability is quite skewed. You will see 7 by 10 for head and 3 by 10 for tail. But since when you are increasing the number of experiments, you will see that this S1, S2 has, and when you get to, let's suppose, S3, which has 10k experiments, this will be more closer to the actual distribution. Okay, and then we have, let's suppose, 100k, this will be more closer. But when we will get exactly this, we never know. Okay, because these things are infinite. Okay, and then to know the actual distribution, we will never get it. But with the more samples, with the more examples, we're getting more proof. We're getting more toward the solution. How many of you understood this part? This is really important in probability. Zakir understood? Okay. So what I'm saying is that you have a distribution and you are performing experimentation, or basically sampling, and to get near to that distribution, to get to that actual distribution that's underneath that. That's why these companies or whatever you are seeing, they are very, very data hungry. They need huge amounts of data. Why? Because there is the actual distribution. There is your behavior. Your behavior can be modeled as a probability process. Okay, what is your behavior for the whole day? So let's suppose I'll just take one thing, clothes. Buying of your clothes will follow a distribution. Okay, let's suppose Rian is buying some clothes, or maybe I am buying some clothes, Zakir is buying some clothes. So buying of these clothes, there is a limited number of clothes that you buy. You'll probably buy pants, and you buy shirts. Okay, you buy shorts, jeans, or whatever there is, and then within the pants you have something, within the shirts you have some brand. Okay, you buy these things. And now if I collect all this data, so basically what it will have, it is a probability distribution. If you think it as in terms of probability, there is an underlying distribution which generates this, and it is based on the knowledge that probably Priyan has, the emotional influence he has, or the things that what is he seeing in the society. All these factors do influence these decisions. Okay, when they influence the decisions, and then when he sees something online, and when he goes to the outside market, what he'll do is he'll buy a particular pant. Now if we have, as a company, let's suppose I am running some Amazon XYZ. It's a new company that we launched. So what I am having is, I want to research on the clothes. So what I'll do is, in that particular area, I'll see the probability distribution that each of you guys are following, because there's underlying probability distribution. The more data I get about you, the more I can guess about the probability distribution that is generating this. And you probably might not know why you're taking a certain decision, but probability models will tell you why you're taking a certain decision. Why? Because they get enough data, and they unreveal that underlying distribution slowly and slowly. And once we get enough, and probably we'll get to know about 90% of the choices that you'll make. That's why we need more data. To need more data, because we are trying to get the underlying distribution. And now we have no way. There are two ways basically to solve the problem. The first way is to know all these uncertain variables, to know all these unknowns which were not known to us, and get their values, exact values. The second approach is get enough data, get a lot of data. Okay, there are two things to make you learn. I can just give you a set of bunch of rules, so I can tell you, oh, if you have to identify this thing, these are a set of rules. But if you have a lot of humongous amount of rules, let's suppose there are 10,000 rules, so it is better to show you a lot of data. If you have a lot of data, then what you can do, you basically try to get this distribution. How many of you understood? This is very important probability. So if you understood this, I'll be probably thinking that you are in that path of understanding probability. So why are these probabilistic modeling performing really better in the real world? Why do they perform really better? Because I told you there are two ways to learn. There are two ways to learn. The first way is to know all the unknowns. Whatever the unknowns are, know them. The first thing is we have to know these unknowns in itself. There is what is called as compound ignorance. So what the first thing is, we don't know what are the things that impact this. What are the things that impact the decision of Rian? So if Rian is buying a shirt, so what are the decisions that impact that? So first I have to know these things. Okay, probably there will be hundreds of thousands and thousands of things that impact the Rian's decision. Okay, and then once I know what are the things that impact, then I need to have their values as well. I need to quantify these things. If I cannot do this, and this looks a very tedious process, so what I'm seeing is I cannot basically see this, but what I can do is, the second way is get large corpus of data. Now I assume that you know corpus, so get a lot of data. Get a lot of data and keep on researching on Rian, and see his behavioral patterns, see how he purchases, what is the community he lives in, and know all the details. And then what we try to do in both of these ways, in this way, what we basically try to do is we try to get to the real probability distribution. So we try to get to near that, which generates it. So every process that is there, it has an underlying probability distribution, and there are these uncertainties which we cannot know. Or maybe if we have like God level power, so God level power, God can do this, because he can know all the unknowns. That's what God by definition means. Okay, so that is why here, if Rian is buying something, God knows what are the factors that affect his decision, and what are the values of these factors. Okay, let's suppose Rian wants to mix in with the society. This is one of the factors. Rian has less budget, let's suppose, and Rian has all these factors in here. And due to these factors, that's why he chose to buy a certain type of a pant, certain type of a shirt. This is one type of method that we could have used to get to know that what Rian will buy next. But the problem is that there are a lot of factors. Not hundreds are very less. I'm saying there are thousands and billions of factors will be there. That probably for humans it will be impossible to know. And now the second thing is, what you can do is, the best shot that you have is collect more data about Rian. The more data you will get, the more closer you will get to this actual distribution. Okay, the more data you will have, and slowly they'll try to unmask it. Okay, they'll collect your data pixel by pixel probably, and to create a full image, they'll collect this pixel by pixel. And once you are fully online, and then you will see like really good recommendations. Why? Because now algorithm is trying to unveil things one by one. That's what this probability distribution basically, this sampling is. Okay, so why am I bringing you this? So the whole connection was this, because we are trying to estimate these averages. this weighted average. So if you see this, why are we bringing the expectation? So expectation here assumes that we know this real probability distribution. So this is the weights. So again, I wrote it probably here. Somewhere I wrote it here. Huh? If you see this, so this is my PMF. So this PMF I would not be able to know, but we assume that there is some underlying distribution that is there, and then we give the values to this. Okay, and you can easily lie with probability. Okay, this is very easy way to lie. So sometimes you will see the average written on a packet, the average number of calories that you would get is this much. Okay, it's very easy to lie with averages. That's why people do care about expected values. This is just a food for thought. Probably you can research on this topic. Okay, everything should not be said. Otherwise, I'll be spoon feeding you everything. So what I'm saying is these expected values become averages, but when you actually know the actual probability distribution, but you do not know now. That's why they are called expectation. This is our expectation. If you know everything about the data, then you will have an average. So you'll average it out. Okay, but the expected values you don't know the whole data. Now what you have access to is some samples of the data, and then you'll just do the weighted average of this. How many of you understood this, the importance of these expected values? They basically, we want to get average. So what is average? So average is the central tendency. Central tendency. So, but as you know that we have lack of knowledge and there are some unknowns which we can't know, then we brought these expected values. We brought these expectations. Okay, that's why these expectations are brought. Average and expectations are different, but expectations do approach the average if you have sort of knowledge of all these things, knowledge of all these samples. Probably you have this population. Okay, that's why we call this an expectation. Expectations, they're entirely different, and do not think them it will be a sample. Let's suppose in a roll of a die, if you expect a value, it is not that you will get that value. Okay, so expectation is somewhat different. Let's say this is a really good point. I just am about to discuss. So we have these expectations. So sometimes expectations are things that won't even appear. Okay, let's suppose you have this 1, 2, 3, 4, 5, 6 on a die. Okay, now if I roll a die, let's suppose if I roll a die, so what will happen is one of the numbers will appear. Okay, let's suppose each of these have probability 1 by 6. So if you compute the expectation of this x, let's suppose this is a random variable x. So what will be the expectation? 1 multiplied by 1 by 6 plus 2 multiplied by 1 by 6 and so on. So this will be equal to 1 by 6 taking it common. This will be 1 plus 2 till 6. So this will be 7 by 3. Okay, 7 by 3. 7. This will be equal to 7 by 3 multiplied by 1 by 6. This is 7 by 18. I think this is. Can you calculate it? I think I wrote something is wrong. Okay, whatever the number is. So I think this should have been the higher number though. This is 7. 1 by 2, that is 7 into 6. Huh? That's what I say. This is 7 into 6 divided by 2 multiplied by 1 by 6. So this is 7 by 2. This is 3.5. Okay. So the number we got the expected value as 3.5. So does it mean 3.5 will appear? So never ever will you get this 3.5. So when you roll this die, you will never get this 3.5 basically. So but what is this expected value telling you then? Can somebody answer it? If we are not getting this number, so what is this telling you then? Anybody? Just make an attempt. Rian, what is this number telling you then?
पता नहीं sir.
Again, it'll tell tendencies, central tendency. This is not a thing that you will actually get. So you probably might not get, as you saw it clearly over here. You might not get it. But the thing is, this is the tendency that it will go because this is the higher probability. If you see why is this number having a higher probability, let me show you. Let's suppose this 1, 2, 3, 4, 5, and 6. So now you see that this 1 and 6 they are quite high. Okay, so if you sort of like if everything has same probability, but still what you will get is, so when you sum up these numbers, so okay, whenever you get number, sometimes you will get 2, sometimes you will get 3, sometimes you will get 5, sometimes you will get 6, but the central and the less error they will have is at 3.5. Everybody tends to get at 3.5. Okay, that's a tendency they have. Okay, this is not an exact will get it. So that's the rough idea I have. So that's why I'm saying that this is summarizing. It probably you might not get the exact same number, but I think it will give you the tendency that the number has. Okay, if you roll a die, probably you will get around, like, you can get what, you can get 2, you can get 3, but overall what you will get is, overall you will get this a number closer to 3.5. Okay, so sometimes you will get 2, sometimes you will get 3, but you can clearly see that. So if you sum up all these numbers, okay, if 1 will appear, so 1 will appear 1/6 at a times, okay, this 2 will appear 1/6 at times, and 3, and so on, every number will appear 1/6 at times. But if you want to see which number will appear, like where will they tend to, and you will see that everybody will have they'll be closer to this 3.5 at average. And all the numbers, if you, let's suppose, take this expectation number 4, so you will see that this 4 will have more error. Coming to the error thing, so let's say what I'm saying is, you are saying that my expectation is this number 4. So if you perform the experiments with this, so you will get a high measure of error. So if you want to take the average, then if you want to see, let's suppose we have this we got some 2, we got 3, then we got 4, then we got 5, and then we got again 1, 2, something, and you collect the data. So what you can see, if you subtract these numbers from, if you subtract the average of these numbers, so whatever you got, you subtract the average of these numbers from 4, you'll get some number, let's suppose 4 minus whatever average of these numbers was, or weighted average. So you'll compute something, let's suppose x. So if you take that 3.5 minus that x, and you will see always this number will be less. So that's what I'm saying. So tendency will be this. So anyway, if you are taking this 4, so if you take this average, weighted average, whatever you like, because you have some samples, and you compute the average. So whenever you have this number and you subtract it with the average that you got of the experiment, okay, then you have this 3.5, the expected average, the expected number basically, and you compute it with the average that you got experiment, and this will be less. But experiment should be large enough. So they should not be like you just take 10 trials, you will just take 1 trial, and you will see no. If you take 1 trial, you got 3, and you will see that this 3.5 and minus 3 is equal to 0.5. But in the second experiment, let's suppose you got 5, and that's why you have to do nth number experiment. That's what probability is. So probability won't be like in the first to go, it will be right. So that's why we have to perform nth number experiments. Okay, and this expected number, do not think that this will appear on the die or this will happen in the real world. This is the tendency that it shows. Okay, the least error where we'll get. So this is the number. So if you have to let's suppose bet, and you'll have to bet around these things. So you'll see that the high thing is that 3.5 probability, 3.5 expectation basically means the error margin is less. So number are basically tending to that. Okay, that's why if you just draw this curve even, so I think each experiment, if you draw this, we got some curve like this. So that's why we have this mean over here. So mean has high tendency that actually we won't be able to get this number, but the numbers that we'll be getting will be around that maximum of the times. And you can clearly see 1, let's suppose if you get this 1/6 at times, and 6 you will get the 6 1/6 at times. Okay, if you get 1 or if you get 6, still like we are saying that central tendency is this 3.5. Okay, that's why this is an average number of these. And do not get confused, this 3.5 will be a number which will sort of appear on the die. I have seen many of the people just using it, and within even books they have not explained the thing. The expectation is not the thing that you will see actually in the experiment. This is just an expectation. That's why it's called expectation. I hope it got somewhat clear, and the more you will probably practice some problems, and the more you will learn about these things, and these things will get slowly and slowly clearer to you. Is it clear? Okay, nice. Now moving on to different properties of expectation. Okay, so what are the different? So the first thing is that, so if you have this expectation, I hope that you got some clarity on the expectations. So now expectations, they can be thought as average. How, when is this equal to average? If we know the underlying probability distribution. Okay, some summary points I would like to write about this expectation. The first thing is, we never have enough data. Okay, so we have a real PMF, that is the underlying distribution, distributions, and by sampling, so by sampling we try to uncover it. I hope that you got the reason. Why do we do a lot of sampling? Because there are hundreds and billions of unknowns that we cannot know. So it's better to get more samples so that to get to this real. And what is this PMF and what is this expectation? So expectation is just a number. It's a number which tries to summarize. A random variable. So again, just for the sake of clarity, so let's suppose here we have some 10 people. Let's say we are 10 people. Each of people have some money in their pocket. Somebody has 5 rupees, somebody has 10 rupees, somebody has, let's suppose, 13 rupees, 15 rupees, 16, 2 rupees, 1 rupees, and 6 rupees. So how many are these? So 4 rupees and 2 rupees. I think these are 10, whatever it is. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So these many rupees we have. So what is the meaning of average over here? So whatever gist you get in the average, that's the same with the expectations. I'm not saying they are same. I'm saying that different concepts. But see, average does not mean that the number belongs here. So if you let's compute the average of this. So this number will be coming, let's suppose, somewhat around less than 16 and greater than 2. Okay, so let's suppose I'll write it 8.6. This is not the right number, so I'm just giving you. This 8.6 never appeared in this. See it here over here. There is no 8.6. But what it tells you something about, it summarizes this somehow. It says that everybody's number tends to that. Okay, so at average, if you take an error rate of all the numbers, the least error you will get it is 8.6. Okay, that's how we take average. So we say the average height of a person in India is, let's suppose, 5 feet 2 inches or something like this. Does it mean that if I take a person, he'll have this height? Or probably a person won't have this height, if you take a sample. But this gives a tendency. This tells you what is the maximum error. So whatever you understand by the average, that's the same thing you should understand by the expectation. It is not the outcome. This basically is a variable that summarizes that thing. You get an idea. Okay, what should I look for? Okay, what are the things that I should expect? That's why it's called expectation. Okay, so let's suppose if you are going to marry someday, inshallah, hopefully soon. So that day, if you you have collected some data and you want to see the height of a girl, so what should you expect? So if you have a lot of data, so you'll say that I expect this height. So probably this won't be the exact value, but that's the expectation. That thing will have the least error. Even philosophically or mathematically, that's even justified. This average is not a number that is among them. It can be, even the number can be in them, but it is not necessary that number will be there. So but what is giving, it is setting you an expectation. So you are getting an expectation. That's what it is summarizing this data. Somehow we are summarizing the data. That's why we brought the concepts of expectations. Average is when we have access to hold the data. Then expectation is when we do not know the underlying distribution and we collect more samples and try to expect the things. Okay, but to how many of you is this clear now? So what's the real meaning of expectations? Rian, clear?
Yes, sir.
Okay. Okay. So this expectation is just a number which tries to summarize this random variable. They are somewhat similar like averages, or sometimes we also call them a center of mass. So why is this so? Because if you have seen, let's suppose object, if you have done some +1 or +2 level physics, so there you find a center of mass of different objects, or maybe a whole system of objects is there, and then you try to find a center of mass. Center of mass basically in simple terms is why do you balance an object? Okay, why do you balance? Let's suppose if you have a stick like this and you put some mass over here and then something over here, okay, something like this, and then you are saying that where should I put my finger underneath it so that I'll balance the system. Okay, so that's why it's again the weighted. If you see, you have to again take the consideration of weights, and then you will say, okay, I have to be distant. My expectation is this much. So wherever the value will be, let's suppose you will balance it somewhere around here. So here we have a lot of mass, so somehow you have to go, let's suppose, till here, so somehow till here. Okay, not even exactly here, so we can have here, because you have to like somehow balance it out. Left hand side should be equal to the right hand side's mass, and that's why it's called center of mass. Okay, where the object will get balanced. That's why this is somewhat related to expectation. Okay, you again take the same weighted sum over here. Okay, what is writing is I'm writing the expectations. So would not know the real PMF. I'm just summarizing whatever we saw so far, and that we have underlying distribution. So by sampling, we try to estimate this. We try to uncover this distribution. Okay, and this is a number which basically summarizes the things. And then I said I gave you a food for thought. Then you can lie with averages. So you can lie with averages. You can lie with averages, but you cannot lie with expectations. Because expectations are the thing that will mathematical expectation is something different. So the expectation word that is in the English, it has a meaning that you are expecting something. Okay, and in here expectation basically means that this is mathematically what you expect. There is a like philosophical difference which probably we'll discuss some other day. But please look over this, how you can lie with average and how cannot you lie with the expectations. Okay, if you somehow see these on the packets that average type of this, the average let's suppose they are selling some food packet and they're saying average amount of protein that you will get is this much, and probably that's a big red flag, and see there is some problem, because with average you can easily lie. And within the school, let's suppose the average amount of students that are like per teacher or something like that is this much. Okay, and then you will see there is a ratio of 4:1 teachers at average. So again, you can lie it on here, but expectation, they uncover the details more. But I don't want to give every detail because again, I want you guys to think about these, what am I speaking here. Okay, now let's see, let's write this formula. Expectation of x is equal to, this is for discrete random variables. There is a lot to talk, but I have to compress this knowledge somehow. I can just talk about expectation in probably 5-6 lectures. We can just have a discussion on expectations, but in the interest of time, we have to shorten these discussions and have to present them in a succinct way. And that's again again an art that probably I like a lot. I is equal to 1 to, let's suppose, some n. So this is what you have to remember. This is just for the formulation. If you have to compute the things, then you use this formula. Okay, then there is a topic that I wanted to cover is expectation of a function of a random variable. So expectation of a function of random variable. For this, I'll start an example. I have an example written. Give me 1 sec. The example goes like this. So there is, let's suppose, some sample space over here. There is some sample space. Okay, and you know that what is a random variable. So random variable is nothing, it just takes the sample space and maps it to some number. Okay, now let's suppose we have some numbers over here. So we have numbers, I'll take the exact values. So numbers are 5, 4, 3 and 2. Okay, these are the numbers that we are mapping the sample space onto these numbers. There are some random variable, let's call this random variable x. Okay, we'll call this random variable x, small x over here. Small x is the value that is taken by this big X. Big X is the random variable actually. So with this sample space, let's suppose there is a 0.4 probability it will get mapped to this. Now we are defining what is called as PMF. Okay, PMF is basically giving these values to these numbers. This is 0.3 and this over here is 0.2 and then we have this is 0.1. Okay, so now you can clearly see this. So there we have a sample space, then we have a random variable x. So here this is the outcomes of the random variable or the values that a random variable can take. Now what I can do is I'm defining a function. See the you have to understand this first. So understand the setting first. So here I'll somehow map, I'll have a function, call it g. So that g will take this as input. That will take the output of the random variable. Whatever the random variable take the values, it will take input as that and then maybe convert into some other number. Let's call, there are two numbers, 4 and 3. Okay, so let's say what I'm saying is if I give g of 5, so g of 5 will be mapped to 4. Okay, so if I say g of 4, it will be again mapped to 4. If I say g of 3, it will map to 3. G of 2, it will be mapped to 2. Okay, this again can be thought as a random variable. Okay, now we have again a mapping, so this is mapped somewhat to this. Okay, or this can be thought as a function. So random variable and function are basically the same things. So what is the random? It's a function basically which map is the sample space to some number. So here I had a random variable capital X. So here this is a function, or it can be thought as a different random variable. So let's suppose I have an expectation of X. So to me, I have been given X, that is a random variable. X is a, let's write it, X is a random variable. And I have been given its PMF also, P of X. So this is given to me. Both of these things are given. Everybody with me so far?
Yes, sir.
Okay. Now what I want to do is, I want to find E of Y. What is E of Y? Expectation of Y. This is expectation of G of X. Okay. So this G of X can be again thought of a random variable Y. I can think this as Y. These are the values. This again is a random variable. Okay. So this G basically is a random variable. So which takes this as towards this. Okay. So what are the methods? So how I can compute this expectation of this Y? So given to me is X. So and I have been given P of X, that this is PMF and this is the random variable. So easily if I have to compute expectation of X, that is easy. So I'll just compute summation of X goes from 1 to whatever value it is, n. Okay, and this is xi and P of X given X. So this is the PMF. So basically this is also given to me. So basically if I can compute it, it's given to me. So the point is that I have to compute this E of Y. So okay, let's compute this. So what I can do is I can average. I can use the concept of averaging over. So this is my method 1. Method 1. There will be no calculation difference, but there will be conceptual difference. Okay, see how I'll calculate it. So basically I have to compute, I have to see this expectation of Y. Okay, that's my variable. So what I'll do is I'll take this 3. Okay, I'll take this 3 and then I'll see what is the probability. So this 3, if you see it over here, so this 3 is generated by this 3 and 2. Okay, so this 3 is generated by this 3 and 2. So now the probability of this 3 and 2 is respectively 0.1 and 0.3. So how I can write it? So I can average 2 like this. So this getting this 3 is having the probability of 0.1 plus getting this 3 is having the probability of 0.2 also. Okay, that's how I'm writing it, because this 3 I got by this 3 and 2, and they have probability 0.1 and 0.2 respectively. Now I'm just averaging it out. Okay, so I'm writing this 3 multiplying it by 0.2, then I'm writing the 3 multiplying it by 0.1. Now I'll take the number 4. This number 4 came from this 4 and this 5. So what I can do is I got this 4 from this 0.3 and I got this 4 with the probability 0.4. Okay, I'm just averaging it out, averaging out the probabilities. So then this plus 4 multiplied by 0.3 plus 4 multiplied by 0.5. So this is my E of y. Okay, so what is the definition of E of y? Basically, I had to take what I just did is I took whatever the value of y was. Okay, I saw how did I got these. I got these values by these two things. Okay, then I multiplied with the corresponding probabilities for this 3, because this 3 has probability this and this 4 has probability this and this. Okay, this is one. I just average it over. That's the one thing. Other thing can be, you can directly take it. You can see this 3 I got from these two sums. Okay, probably this is the averaging over I'll say x. This is when I average over x, because I'm taking the values of x, averaging over x, and I have other thing that is averaging over y, method 2. So method 2 over here is, just bear with me for a couple of minutes, you'll understand it fully. So method 2 is averaging over y. So averaging over y, averaging over y. So now I won't see this. So I won't see this variable altogether. I won't see this x. I'll just see y. So what I'll do is 3 and then directly go to the probabilities 0.2 and 0.1. That's 0.3. I'll just do one thing. So 0.3 multiplied by this is 0.1 plus 0.2, because that's the probability of getting this. Okay, the probability of getting this is this plus this, and probability of getting this is this plus this. Okay, so plus 0.4 multiplied by getting the probability is 0.4 plus 0.3, 0.4 plus 0.3. If you see both of these methods, if you see mathematically, they pretty much look similar. Okay, they both of these things look pretty much similar. So why do they look similar? Because the calculations are pretty much similar, but conceptually there's a huge difference. So what is the difference between that? The first thing that we did is this, and the second thing we did is this. So in the first thing what I did is, so I took this 3, okay, I averaged onto x. So what was the averaging over x? So I went to the x. So I saw this 3 I got by this 2, and then I got this 3 by this 3, and I wrote the corresponding probability. See the method. So in the method 1, I took this 3. The 1 point was, I'll see how did I get it. I got it by 2. Okay, I got it by 2. Then I'll write the corresponding probability. I'll again come back to 3. I'll see how did I got this 3. I got this 3 by this 3 also. Okay, so I'll write the corresponding probability. That's why I'm saying averaging over x. So the first method I named averaging over x, because I'm seeing the x over here. I'm just seeing my y, and then I'm going through the x. I'm saying, okay, this is the x which I had, and this is where I got it from. The second method was directly averaging over the y. Okay, see the y, okay, and directly get the probabilities and add them up. Do not go separately. First, in the first method, I went to this path, then I went to this path. In the second go, what I did is I just saw what are the numbers that gave me this. So this 0.1, this 0.2. So they gave this rise to this 3. Basically 3 and 2, they gave rise to directly this 3. I'll just write the probabilities. So I'll just write them different in mathematics. Okay, this method is basically the simple average. This is simple averaging. Okay, now if you see over here, so I can just write the method first rather. So I'll write it like this. So E of y, how did I calculate it? I calculated it with like this, E of g of x, because I went through x, or maybe E of g of x was basically y. So this is E of y. So I just compute. I had to compute this. If I had 3, so 3 was being given by 3 and 2, and then I wrote their probabilities. So I can write it E of g of x is like this. E of y is basically E of g of x. So how I can write it now? This is summation over x. Okay, g of x. So I took the value g of x and then multiplied with the probability p of x. So this basically whatever the value of x was. So again I'll explain this. So this part I want to explain because I think there is a need of explanation over here. Am I audible though? Everybody with me?
सर मेथड 2 में शायद आएगा.
So correction here that was I wrote instead of 3 I wrote 0.3. So what I'm saying is, so here we had this number 3. Okay, so here we had this number 3. In the method 2 we had this number 3. Okay, now we are averaging over y. So I'm just caring about y. Okay, I'm just taking which are the numbers that gave rise to this 3. So that these probabilities are this 0.1 and 0.2. That's why I just added these probabilities 0.1 plus 0.2. That's how I got to 3. Okay, I'm just averaging over the y. And then this 4, how I got this 4? By this 0.3 and by this 0.4. That's what I'm writing. 4 multiplied by 0.4 plus 0.3. Okay, that's a wrong thing. I wrote 0.3 and 0.5. These actually are numbers. So in here I also had a made mistake. I wrote 0.5. Okay, so if you see in the first method, what we did, we averaged over x. We went to the x and saw what are the numbers that gave rise to this. This 3 was being given rise to this 2 and this 3. So I wrote the corresponding probabilities. I wrote 3 multiplied by 0.1 and 3 multiplied by, I took all the paths. So in the second method, I did not take this path. I just saw, so what are the things that gave rise to this? I'll add them together. So I add and I landed here. And I'll add, I landed here. And in the first method, what I did is, I saw, so which are the things that gave rise to it? I'll say 4, I came to this path. And the second 4, I came from this path. So that's what I wrote it. So here I wrote it, E of y basically is equal to E of g of x. So this is method 1. So method 1. So E of y basically is E of g of x, because g of x gives rise to y. That's what I wrote in the diagram itself. So g of this values x gives rise to, g of x gives value to rise this y. That's what I wrote. So if I wrote E of y, that basically says E of g of x. So how I can write it? I said that this is summation of g of x. So whatever, if I do not, I can write it like this. So E of y can be written like this. E of y can be written like this. So this can be summation over values of y multiplied by PMF of y. Okay, this is PMF of y. So, but I do not have access to this. Okay, I have to compute this. Basically, I can compute this. But what I can do is, I can just use this probability of this, probability mass function of x, and then I'll just use this function. I'll use this g of x. That's what I wanted to say. So in here, I just will explain this again by the same example. So here, if you see this method 1. So this method 1 of averaging over x. Okay, so what we have done in there is, so we just took the values. So here, the same thing will be there. Let me just see if the probabilities are correct. I think the probabilities are right. So we'll just average it over this. So now you will take this 3, okay, and this 0.1 is basically g of that 3 and g of whatever the value we gave. So this is that g of, so example over here is this. So g of this. So here we have this 3. So g of 2 and multiplied by g of 3. So it will be something like this. So 3 multiplied by g of, this is the number that gave rise to that. Okay, that's why I'm writing the PMF of that. So g of 2 and g of 3. Okay, so g of 2 and g of 3. So and g of 3. So these two numbers give rise to this 3. These are the two numbers which give rise to this 3, and this also gives rise 3. That's why I wrote this g of x. Then what is the probability corresponding to that? If I know probability of this and probability of this, that basically is 0.2 and 0.3. So if you see,
Sir, did you unpause the recording?
Yes.
Okay.
Okay, thank you for reminding. So what I'm saying over here is, so g of this x. So g of x was this value. So g of x was these values. Okay, so g of 5 is 4, g of 4 is 4, g of 3 is 3, g of 2 is 2. Okay, so I am writing g of x. So first compute this. What is the number that gets mapped to this? So if you see this, so these are the numbers. So this 2 and this 3 got mapped to 3. That's why I wrote 3 multiplied by something plus 3 multiplied by something. So this is g of 2 and this is g of 3. And then what is the something? That is PMF. Okay, and PMF of that x. So what is the number? What is the PMF of 2? That is this. PMF of 2 is PMF of this 2 is 0.1 and PMF of 3 is 0.2. That's what I wrote, is 0.1 and 0.2. So this is 0.1 and this is 0.2. Did you understood this though? I'm just scribbling over here. I'll just take this, just summarize it in maybe 2 minutes again. Give me 2 minutes, it will be clear, because I had to switch the page again. So this is the basically the experimentation that is there. Okay, so what I'm saying is the meaning. I'm just trying to explain the meaning of this. So I'm telling you that just take these numbers. So g of 5 basically is 4, g of 4 is 4, g of 3 is 3, and g of 2 is also 3. So this is this function. So g of 3. So what I can write is, so I can write g of 5 and plus what are the probability of 5 was when it was in the random variable x, plus g of 4 multiplied by probability of x takes this value 4. and so on. So what is g of 5? G of 5 is this 4. Okay, and if you see this, g of 4 is again this 4. Similarly, I am writing this. So g of 5 over here, if you see this is 4. And so g of 5 is, this gives rise to 4 multiplied by the probability of this, that is 0.5. Then plus this g of 4 again is 4 multiplied by this 0.3. Okay, that's the method 1 we did. So in the method 1 we just took the numbers and we just took the number 3.1, 3.24. That's what I said, that the easiest thing is you don't have to compute this PMF of y now. So if you somehow know this g of x, that you already know, and if you know the PMF of x, you can just write the this formula for expectations. Okay, so you don't need to compute this p of y. You don't need to compute this. You don't need to compute this to compute e of y. You can directly go it. So e of y is directly equal to summation of x and take the g of x. So instead, actually, we will write y over here. So p of x over x. So usually, if we have to compute PMF of y, that was equal to PMF of y multiplied by this. So this is what we actually had to compute. We have been given y, we had to compute PMF of y. But you again saw that, so we can just use this g of x and then directly use the PMF of x variable that has been given with us. So this is the really important thing. So why is it important? So let's suppose if you have to compute expectation of x square. So this is nothing but x square multiplied by PMF of x. Sum it over x. This is really easy now. Otherwise, you had to go through this. You had to just compute first this y, then PMF of y, and then multiply them together, then add. So if you have this function, so that's why I wrote the name of the topic is expectation of function of a random variable. So what is the expectation? If we apply a function onto a random variable, so directly you can just use that function and multiply it with the corresponding PMF of given x, the basically the domain, the input domain. I hope this is clear now. Is it clear?
Yes, sir.
I'll stop the recording here. I'll take the question. There is a lot to discuss in expectation and this probability, but I want you to have really good grounding in this topic. That's why we're covering in a bit of a detail.